Okay, in this lecture, we're going to be looking at how to calculate empirical formula, a molecular formula of a compound. So what are these to begin with? Well, the empirical formula is the simplest ratio of atoms. So for instance, if we look at this molecule below here that shows how all the atoms are bonded together, we can count and see that there are 6 carbons and there are 6 hydrogens. Well, that is the formula of the molecule, and we've already learned about that. The formula of a molecule is the ratio of atoms. So for benzene, the formula is C6H6. Now, what is the simplest ratio of this? Well, we want to get these numbers to be as small as possible, but still the same proportions. If we divide each of these by 6, we get C6, or we get C1H1, but we don't write the 1, so we get CH. So empirical formula, simplest ratio of atoms. Molecular formula, the actual ratio of atoms. You might ask, well, why do we even have empirical formula when there is the molecular formula? And the answer is when you first discover the formula of a compound by experimental data, more than likely, if you're doing this without mass spectrometry, you're going to get the empirical formula. You're going to get the lowest ratio. And then you have to build up and figure out from there what is the ratio of atoms. Okay, so let's take a look here. Calculating the empirical formula for mass percent. Here's how you go about it. You assume the mass percent of each element is the gram mass of that element. So if you have 90% carbon, you assume that you have 90 grams of carbon. And if you have 10% hydrogen, you have 10 grams of hydrogen. Then you convert the mass of each element into moles of the element. And we've seen that before. You need the molar mass. How do you get the molar mass of an element? You use your periodic table. Then you divide each mole of the element by the lowest to get a simpler ratio, and then you adjust accordingly. Sometimes you don't have to adjust, sometimes you do. When do you have to adjust? Well, when one of the ratios ends up being a fraction, you're going to have to adjust. So let's take a look at an example. So, what is the empirical formula of a substance that is 59 or 52.9% aluminum by mass, and the rest is oxygen? So of course, to figure out the rest being oxygen, we would have to take 100 minus 52.9 to get the amount of oxygen. So we have 100 grams of substance, 52.9 of it is aluminum. How much is oxygen? 100 minus the 52.9, we get 47.1 grams of oxygen. So again, we're going to assume that we have 100 grams of the substance, and of that 100 grams, this mass percent means that we have 52.9 grams of aluminum out of 100 grams of substance. That's the definition of percentage. We figured out that the rest is 47.1%, and that's going to be 47.1 grams of oxygen out of 100 grams of the substance. Step 2, take these masses and convert them into moles. So here I use the molar mass of aluminum, which I look at the periodic table to find, and we can convert the 52.9 grams of aluminum into moles of aluminum. And you can see that this seems to be about the correct number with these two numbers, because I have basically 53 divided by 27, which should give me around 2. And then here we have 48.1 grams of oxygen times the molar mass of oxygen. Now, why does the gram go on the bottom? So these cancel. So we end up getting about 3 moles of oxygen, because 47 divided by 16 should be around 3. So if I had 100 grams of substance, I would have 1.961 moles of aluminum and 2.944 moles of oxygen. Now remember, the formula, these ratios can be atoms or they can be moles of atoms. We're going to assume that they're now atoms. So we have aluminum 1.961, oxygen 2.944. Okay, so are these close enough to round? And the answer is probably not. This is good to the 6, this is good to the 4, and considering how precise our data is, we should not round this quite yet. So, but maybe. So if we rounded it, we'd get aluminum 2, oxygen 3. Well, let's see if we find out that that really does work. What I'm going to do is I'm going to divide each of these by 1.961. So what is 1.961 divided by 1.961? It's 1. What is 2.944 divided by 1.961? It's 1.50. Okay, so here I don't like having a fraction for my subscript for an element. You can't have 1.5 oxygens. So what do? You're going to multiply both of these by 2. So this is the adjustment. So we get aluminum 2, oxygen 3.00. And I got to tell you, when I look at these numbers here, I'm much more satisfied with my answer than having to round here. Here I'm unsure whether or not rounding will make it work. Here I'm absolutely sure that aluminum should be 2, because here, if we take a look, 1.961 divided by 1.961 is exactly 1. And then here when I double it, what's 1 doubled? It's exactly 2. And we can see that our oxygen 3.00, which is good to 3 zig figs, certainly rounds to 3. Okay, so this is the empirical formula of the substance. Now, let's look at calculated empirical formula and molecular formula. So in general, here's how you do it. First, you calculate the empirical formula. And this is a very shortened description of how you do it. You get masses of the elements, turn them into moles of the elements. Then you take the moles of the elements and turn them into ratios of atoms in the formula. To get the molecular formula, you take the molar mass of your compound divided by the molar mass of the empirical formula. So that means you have to be given the molar mass of the compound. The molar mass of the empirical formula, you figure from your answer above what the empirical formula is. And you get what I call a multiplier. Then you take the empirical formula times the multiplier to get the molecular formula. So here's an example. Analysis shows that the molar mass of a compound is 78.11 grams. And it is 92.26% carbon and the rest hydrogen. Determine the empirical formula and molecular formula. So here's that data again, 78.11 grams, that's the molar mass. That means 1 mole is 78.11 grams. It's 92.26% carbon and the rest hydrogen. So here is the empirical formula. We're going to assume we have 92.26 grams of carbon and 7.74 grams of hydrogen. These two numbers add up to 100. I'm going to take my grams of carbon and convert it into moles of carbon. So here we go. I'm going to take my grams of hydrogen and turn that into moles of hydrogen. And here we go. Then I use these numbers as my subscript. So the 7.6829, that should be a 29 right there, becomes carbon 7.6829 and hydrogen 7.6786. You can see these numbers are really close to one another. So you can bet your bippy it's going to end up being carbon 1 and hydrogen 1. But just to show you the method, just in case it doesn't end up being a 1-to-1 ratio, I'm going to divide each of these by the smaller of the two. And the reason I divide by the smaller of the two is because I'm sure to get a 1 in my answer. So here, 1.0004 rounds to 1. So I get C1H1, and we don't write the ones in the empirical formula. So this is the empirical formula, 1-to-1. Okay. Now to get the molecular formula, I take the molar mass of the compound. This is given, you can see above, and I divide by the molar mass of the empirical formula. So the molar mass of the empirical formula is the mass of 1 mole of carbon plus the mass of 1 mole of hydrogen, which is 13.018 grams. Now, I take the 78.11, divide it by my 13.018 grams and grams, and I get my multiplier, which happens to be 6. So here I take the empirical formula times the multiplier. And remember, this is really a 1 and this is a 1. So I get C 1 times 6 and H 1 times 6. And the molecular formula is C6H6. Okay, so let's take a look at an example here, calculating a formula from percent composition. So this is just like the problem we just did, but this is another example. In this case, we have 1, 2, 3 elements, not just 2. So the first step to get the empirical formula, we're going to take 60.33 grams of carbon, multiply that by 1 mole of carbon per 12.01 grams of carbon. And we're going to get roughly 5, right? 60.33 divided by 12.01. And we get 5.0233 mole of carbon. Now we're going to take our 5.06% hydrogen and say grams of hydrogen times 1 mole of hydrogen per 1.008 grams of hydrogen. And that's going to be equal to roughly 5. And we're going to get 5.0198. And here we're going to round there. Mole of hydrogen. And then we have 7.82 grams of nitrogen times 1 mole of nitrogen per 14 point, and I have to look this one up. I think it's 0.1, maybe 0.7. It's 0.1. And here you can see that the answer is going to be about 0.5. 7.82 divided by 14.01, and we get 0.5582 mole of nitrogen. Okay, so now what are we going to do? Here's what I'm going to do. I'm going to say I've got carbon 5.0233, hydrogen 5.0198, and nitrogen 0.5582. Now, what am I going to divide by? I'm going to divide each of these by 0.5582. So by doing so, I make sure that the smallest number I'm going to get is going to be 1. Nitrogen will be 1. And here, each of these numbers will be bigger than 1 because when we have the formula of a compound, the smallest number you can have is 1. So we ensure that the smallest number we're going to get is exactly 1 by dividing by the smallest of the numbers for the subscript. So 5.0233 divided by 0.5582. And here we get 8.999. And then we get 5.0198 divided by 0.5582. And we get 8.993. And you can see that this very readily rounds to C9, H9, N. And that's the empirical formula, the simplest ratio. Now, to get the molecular formula, I need the molar mass of C9, H9N. So I'm going to do a little side work here. 12.01 grams times 9 is going to be 98.09 grams. 1.008 grams times 9 is going to be 9.072 grams. And 14.01 grams times 1 is 14.01 grams. And so the molar mass of this is going to be 9.09 plus 9.072 plus 14.01, and I get 121.172 grams. So that's the molar mass of the empirical formula. And here we would be rounding this to here. So to get the molecular formula, I take the molar mass that we're given here. The molar mass is 179.17 grams per mole, divided by, did I do this right? I'm not sure if it's going to work out, I'll be honest with you. 121.172 and 179.17 divided by 121.172, and I get 1.47. So that's my multiplier, if you will. And I got to be honest, there's something a little off about this. And I'm trying to figure out what it is by looking at all of my work here. Let me make sure I did this right. 12 times 9. This is 108.09, not 98. So that's going to change things over here. And let's see if I did all of this right. So 60 divided by 12 is 5. 5 divided by 1 is 5. 7.5. This goes into that 9 times. This goes into that 9 times. That seems reasonable. Okay, and here, hippuric acid has a molar mass of 179.17. I'm going to do a little quick check here. And I want to find out what the molar mass of hippuric acid really is. And indeed, it's 179.17 grams per mole. Okay, so that being the case, this becomes oh, I see what I did wrong. So what happened here, folks? Take a look. Is it pretty clear? So this is a good lesson for you in not reading completely. So what we're going to do is we're going to go ahead and leave the problem here. We're going to cover up the work, but what did I miss? Well, take a look at these numbers here. 60.33 plus 5% plus 7.82%. Does that come close to 100%? No. So what did Tony do? Tony did not read the problem fully and see that the remainder is oxygen. So this is a good lesson. You see me screw up? You see we get a problem here where this multiplier is not a whole number. It should be a 1, a 2, or a 3. And so what's the solution? The solution is Tony screwed up. Okay, so let's try again. So the first thing we're going to do is we're going to take our 60.33 grams of carbon times 1 mole of carbon per 12.01 grams of carbon. And we already have the answer to that. It's 5.0233 mole of carbon. Now we have our 5.06 grams of hydrogen times 1 mole of hydrogen per 1.008 grams of hydrogen, and we get 5.0198 mole of hydrogen. We take our 7.82 grams of nitrogen times 1 mole of nitrogen per 14.01 grams of nitrogen. Where do we get these molar masses from again? That's right, periodic table. And we get 0.55 0.82 mole of nitrogen. So here, this is me keeping track of where I would round if I had to. And then we have to figure out how much oxygen we have. So I'm going to take 100 and subtract from that 60.33 and 5.06 and 7.82. So we get 26.79 grams of oxygen times 1 mole of oxygen per 16.00 grams of oxygen. And we get 1.674, I'm going to call that 4 mole of oxygen. So now we have carbon, 5.0233, hydrogen, 5.0198, nitrogen, 0.5582, oxygen, 1.6744. What am I going to divide by? And the answer is by the smallest of these. 0.5582, 0.5582, 0.5582, and 0.5582. Now we can cut to the chase here, and we know this is C9, H9, N1, and O. Let's find out what this one is. I predict that this will go in about 3 times. 1.6744 divided by 0.5582 is equal to 2.9996, which certainly makes this C9, H9, NO3, and that's the empirical formula. So let's figure out the molar mass of this empirical formula. We have 9 times 12.01. So we have 108.09 grams of carbon. 9 times 1.008. We have 9.072 grams of hydrogen, 14.0 grams of nitrogen, and for the oxygen, 48.00 grams. We add these all up together. And we get 179.172 grams. And that's good to write here. So to get the molecular formula, we take the given here, 179.17 grams per mole, divided by the 179.17 that we have here, and we get 1, and that's our multiplier. So that means our C9, H9, NO3 with a multiplier of 1 becomes C9, H9, NO3. And so this is the molecular formula. So you can see that if the molecular formula cannot be simplified, then it will also be the molecular formula. So what did you learn about all of this? Hopefully you learned, well, the method is to find out the mole of each atom and then put that into a formula and simplify it. And don't read part of the problem, read all of it. Okay. Now, let's take a look at this next part here. Calculating an empirical formula from experimental data. This is called calculating the empirical formula from combining masses. This is where we will start off with for our next lecture. All right, thanks for listening, and I hope you learned something. I learned I better read more carefully.